Hello, my name's John Broadwell, and I'm Embedded Systems and Medical Device Development Consultant at my company Broadwell Consulting Incorporated. Lately, I've been doing some personal development to learn Fusion 360 to add to my services capability to move into low-end prototyping and 3D design that might go with some of the electrical and embedded systems solutions that I provide. One of the fun things that I like working on is robotics, and in order to do that, sometimes it's fun to make custom mechanical assemblies, often around the popular SG90 servo. And in order to do that, often you want to put a gear on that servo. The problem is that you can't 3D print the gear splines because where they connect to the servo, because they have a tendency to shear off from the amount of torque that the servo creates relative to the strength of the 3D print. The solution to that is to use the molded nylon part that comes with the servo and yet connect that to a gear. I'm going to show in this video how to 3D print a gear around the servo horn so that you get both the strength of that horn and the flexibility of a custom designed 3D printed part. I'm not a mechanical engineer by trade, so some of what I do may not be best practices. I'd highly recommend that you go to the Product Design Online YouTube channel or some of the other professionals in order to learn some of the best practices for Fusion. But this certainly has worked good for me, so I wanted to share the technique. I would mention that a lot of what we're going to do today is modeling the servo horn. You can potentially skip this over by going to GrabCAD or one of the other similar ones and downloading a model. However, I'd recommend caution when you're doing this with the SG90 servos because they're kind of a generic lot that come from a lot of different manufacturers. I frequently open one and find that it has a different set of gears or circuit boards or motors than the last one I opened. Similarly, I've had trouble with some of the parts not fitting exactly the way that they should, and I think that's because this particular, not necessarily brand, but class of servos comes from a variety of different manufacturers, and that there tends to be some variation from part to part. So that's why when I use an SG90, I'll buy a lot of 10 of them or 20 of them at the same time, and then build up a design that's specific to the tolerances that I've found on those parts. Finally, before we get started, allow me to plug my products that I sell as an embedded systems engineer. If you're looking for a way to control the servos that you're modeling for today, take a look at the Serial Wombat 18AB chip. It's an I2C connected device that's actually a microcontroller running custom firmware, and it does lots of great servo stuff. It can output pulses for all kinds of servos, including high-speed 300 hertz or faster servos, and also has real-time feedback control so that you can drive a servo based on an input. It has rate limiting, it has motion limiting, all kinds of good stuff. Go back to a default position on loss of communications, all kinds of good stuff for your robotics or other mechatronics projects. Secondly, if you need a way to power your servos, take a look at one of my two servo power boards. They break out the control line separate from the power lines. One of the boards is designed to allow you to power from a battery pack or desktop power supply. The other, for smaller servos like this SG90 for light duty, connects up to a USB power bank. So it's a very convenient way to power your servos separately from your Arduino or Raspberry Pi or whatever power supply, which is always a best practice. So now on to the tutorial. One of the underlooked engineering tools available to many people is a simple flatbed scanner. In my case, my scanner can scan at 1000 dpi, and because it doesn't have a bend to it like a camera lens, it's almost a perfect scan. We're going to start by scanning our servo horn sitting on the scanner, along with a ruler so that we can check the dimensions after we've scanned it. Now that we have our scan, we'll drag it into Inkscape, making sure that Inkscape is set up in millimeters. We're going to embed the file and put it in there. Now we'll use the image of the ruler to draw a reference vector, of which we know the definite size. We'll use that to scale later when we get into Fusion 360. In this case, we're going to make a 40 millimeter line. And we'll drag the image off of that line. We'll go to Path and Trace Bitmap. We'll invert the image so that we get black on white. We can adjust the brightness threshold 410 to get more or less of the image, and then click OK, and close the window. At this point, we have a vector and the bitmap image. We're going to delete the bitmap image. We're going to want to deal with the vectors of this individually, so we're going to go to Path, Break Apart. Currently, the closed paths are filled. We don't want that. So we're going to go to Fill and Stroke, get rid of the fill, and add a black line. Now we have just the outline of the various servo horn vectors. There's a lot of cruft in this picture from the scan. We're going to delete everything that isn't the servo horn. Now we'll select just the vectors that we want and group them, move them aside, and delete any remaining cruft that was in place before. We'll save our file as an SVG to import into Fusion 360. That finishes our workflow, so we'll close Inkscape. We'll create a new project, a new design, and a new component in that design for the servo horn. We'll make this component external because there's a good chance that we might want to use the servo horn again sometime in the future. We'll create a new sketch on the XY plane. And we'll insert the SVG file we created in Inkscape into the sketch. For now, we'll import it with scaling factor of 1, which may or may not be right. We created a 40mm reference line. And looking at the measurement, it's actually 10.574 millimeters, so it's not the right scaling. By dividing the desired value by the actual value, we can get the scaling value we need to make it correct. In this case, 3.78. We'll delete the sketch we imported, and then import it again, adding the 3.78 scaling factor. This time our 40mm reference line turns out to be exactly 40mm, so the sketch is properly scaled. The imported SVG includes a number of closed profiles for the outside shape and all of the holes. So if we wanted to, we could just proceed with this and extrude it and print it on the 3D printer. However, these holes aren't all even, and there may be some error introduced with the trace. Additionally, the outside line is very, very ragged. And what that means is that any shape we create will be unnecessarily complex. This will work against us later when we want to embed it into the gear, especially when we want to add offsets to allow a little bit of clearance for the insertion of the servo horn. So let's go back now and create a more idealized version of this based on the outline that we have. Eventually, we're going to want to throw away the scan. So let's create a new sketch on which we'll do our idealized servo horn. That'll make getting rid of the imported image a lot easier later if it's not mixed in with our same sketch. Eventually, we'll want our part to be properly positioned and symmetrical where appropriate across the X and Y axes. And so in order to do that, we need some points to make sure they're right. It's unlikely that we place this thing perfectly horizontally and vertically on the scanner. And in fact, if we look at it close, we can see it has a slight tilt to it. So we're going to create 3-point circles at the points that are easiest to define outside at the edges, which is the 4 outside connector holes. It's likely that any circle that we draw based on those and then draw lines from the center of the circle from one end to the other are going to be very, very accurate in terms of the rotation of the part. And so we'll use those points to create the axes across the horn. And then after we've sketched our horn, then finally we'll make an adjustment to make sure that those lines are perpendicular and that they are perfectly horizontal and vertical. When we draw lines, you can see the icon on the right that's highlighted in blue near line type. We're going to tell these to be construction lines. And what that means is that we're saying we're never going to actually draw a profile off of those lines. They're just marks that we're putting on the sketch that'll help us orient or create other marks later. This servo horn is symmetrical across the y-axis, but not across the x-axis. There's a different number of holes on the top and the bottom. And that aspect of this design will inform the way we do things. We're going to create the bottom and the top half, but then we'll mirror across the y-axis to make both sides. Doing our three-point circle, it appears that the holes are likely to be exactly 1.0 on a perfect part. So we're going to dimension them that way. And we'll assume that all of the holes are the same size. We'll use the equal constraint to make all of the holes equal sized. It's good practice to make your sketches fully constrained, which means that the lock icon will show up on the sketch. In this case, we're not going to worry about that because some of the places where our lines that we're drawing over the top of what we imported from Inkscape are kind of arbitrary. And so in this case, I'm not going to worry about that. If I was modeling the whole things based on measurements or based on a drawing in a data sheet, then I would try to create a fully constrained sketch. We're going to use the rectangular pattern tool in order to create the series of holes that we see there, but we want to check the spacing between the holes. So I created a three-point circle on the bottom hole, and now I'm going to use the measure tool to see the distance. 5 spaces spanning 10 millimeters means that they're 2 millimeters apart. So we'll use the rectangular pattern tool in order to do that. Generally speaking, it's preferable where you can to use a rectangular feature rather than using the rectangular pattern in the sketch tool. But I want to have a nice clean sketch of the whole part, so we're going to do that here. We'll repeat this procedure for the bottom 7 and the left 2 holes. Finally, for the center hole, we'll base that on a center circle from the intersection of the 2 construction lines rather than a 3-point circle. That's probably a little bit more accurate than the scan that we got. We'll draw a diameter and see what the value comes out to be. The 2.48 is likely to actually be 2.5. That's what I would guess that the nominal value is. So we'll change it to 2.5 and assume that the 0.02 millimeters was an error in our scanning and circle drawing. At this point, we have a perfect example of the holes that we want. Now we have to draw the outside profile. In order to do this, we'll start by tracing the straight lines, and then we'll use arcs to connect the curved lines. Splines might be a little bit more accurate, but the arcs should be plenty good for what we're doing, and they're much easier to work with for me than splines. I'm not that good at splines. We'll model on the left side of the part, and then eventually we'll mirror it across that axis. Right now, the only lines we have that represent that axis are the construction lines on the other sketch. So I'm going to create a couple, one at the top and one at the bottom, that are collinear with those construction lines. That'll help us when we delete the bottom sketch. Now I've got the shape on the left, I'm getting ready to mirror it. I'll take this one hole I've got on the right and convert it to construction. Now we'll select all of the items on the left that are exclusive to the left side and mirror them across our vertical construction line. We mirrored one side to the other, but we didn't get a closed profile. What that means is that some of the points on the lines are not connected to each other. So we'll go around and take a look. Most likely it's on the mirror point. There it is. Those lines should connect, and they didn't. As soon as we close it, now we get a filled-in closed profile. So it looks like our part is complete. Now we can delete the original sketch that came in from the SVG file. Finally, the two construction lines that we have are not horizontal and vertical. So we're going to go through and we're going to constrain a bunch of the items on there to stick to those, and then we'll do a rotation on those lines in order to get them to the proper angle so that they're vertical and horizontal. Now we'll draw a temporary totally vertical line and compare it using the measure tool with one of our construction lines to determine the angle between the two lines. We can see here next to angle under results that it's 0.388 degrees. So now we'll select the entire servo horn and use the move tool to rotate it by that amount. Finally, we'll use a point-to-point translation to move the center of the circle to the origin of the part. Now this part is ready for extrusion. Measurement with calipers indicates that it's 1.35 millimeters thick in the main part. We'll create an offset for the height of the ring that connects up to the servo, which is 2 millimeters high, and move this surface up a little bit. Then we'll model the ring going down. This will be ideal later for when we want to cut this part out of the gear that we want to do. Measurements with calipers indicate the outer ring has a diameter of 6.75 millimeters. And a wall thickness of 1.35 millimeters. Since we've already put an offset on it that's moved this bottom surface up in the air, we can just extrude back to the origin, and that will give us the proper height. At this point, the model is complete. Let's print it and compare it to the original. We'll right-click on the component and choose Save as Mesh, and save it as an STL file to my computer. We'll load it into Cura to slice it and create G-code that we can send to the printer. That slice looks good. Let's save it, send it to the printer. All right, let's print it. Okay, printing's done. Now let's put it on a light table and see how the print compares to the original part. Looks good with the printed part on top. Let's put the original part on top. Looks good too. All right, let's take that and use it for our model. Okay, let's create a new project, a new design, where we will create a gear with the spline gear add-in. I won't go through all the details of that, but we're going to create a 12-tooth gear using that add-in, and it'll be 8 millimeters thick, a pitch of 24 millimeters. There's a ton of pre-existing examples of how to use this tool, so I won't go into it in detail. We'll just get the gear. Now we'll drag in the servo horn that we made before. Since they're both oriented towards the origin, a lot of our work in positioning is already done for us. Now clearly the servo horn is too big, so we're going to make modifications to it. We don't want to modify the original, so we're going to break the link to the original component. Now any changes we make to the servo horn will be limited to within this design and won't propagate back to the original, because we want to keep the original servo horn accurate to the part that we modeled. So we're going to take that servo horn. If you note, I clicked the little round dot next to the servo horn component. That means now that any modifications we make go in that. If we hadn't clicked that, then the sketches we create or whatever would have gone in the overall design. That's not what we want to have happen. So at this point, we're going to select the top of the servo horn and add a sketch to it. Looking at the servo horn, clearly we're going to have to cut it down to make it fit entirely within the gear. We'll plan to use a pair of cutters to cut it off after the second circle. So we're going to also simulate that in the model by just doing a simple cut that along this circle that we're drawing now. We'll make it big enough to go around the entire horizontal set of the horn and then cut it off right there. And that's what we will use as our model for the inside hollow out of that gear. So we'll draw one circle for what we want to keep and a bigger circle around for what we don't, and we will do the cut on the outside circle, going all the way through that part and getting rid of the plastic that we're going to physically cut off with the pliers. Here we see an approximation of what our servo horn is going to look like when we cut the nylon one, and it fits nicely within our gear, so we're in good shape there. Next, we'll make the gear body visible again, and we will use the combine tool. We will choose the gear as the target and the cut up servo horn as the tool, and we will do a cut on those and say OK. So now we've removed some of the plastic from the inside of the gear. If we look on the bottom, we can see that there is in fact a cutout there. And if we go to inspect and go to section analysis, we can do a cross section of the gear, moving through the gear, and we will see where the servo horn is cut out of that. So we will make that servo horn not visible now so that all we're seeing is the plastic of the gear. Now, I don't like those little pins in there. Those look like something that won't print well, and they're definitely going to get in the way when we go to insert the servo horn into the middle of our gear. So let's go into the sketch and just get rid of those pins. And again, we can do that because we have a copy of the servo horn here, not the original, because we broke the external link. So with those holes removed from the servo horn, we have a solid servo horn with no holes, which means that the cut that it makes out of the gear is also a nice, easy contour. So next we know that the thing is going to fit in there really, really tight because it's a perfect fit right now. We're going to use the offset tool on each of the faces that we can see right there and add a 0.3 millimeter offset. That's based on my experience with my plastic and my printer. Your value may be a little bit different. That will make that hole a little bit bigger in every direction, and that guarantees that we'll be able to slide the servo horn into the hole that we print. So the next thing, we know that the servo horn that we used had a hole in the middle, so when we went to cut it out of the gear, it left a chunk in the middle. So we'll use the existing hole profile and cut that all the way through to the gear to get rid of that chunk, and that will also give us a place to be able to get to the servo horn so that we can put a screw in it from the other side of the gear. So we can use that existing profile, and we will just do a cut up to object and use the other side of the gear, and we will be in business here. And there's the hole that we want. That's great. Finally, we'll add a 0.3 millimeter offset to the edge of that hole to make sure that the servo horn cylinder will fit inside of it. And I think from there we should be good. We'll right-click on Spur Gear and select the Save as Mesh command and send the thing to the printer. We'll open the part in Cura, and we're going to slice it twice. We're going to slice it once to get the level, and I looked at this previously, you can see that. At level 25 is when it starts to cover up that hole. So just before then, we're going to want to tell the printer to stop. And so we're going to put an item in here that says we want to do a filament change on layer 25. We're not actually going to do a filament layer change, but it'll make it stop. And your printer may or may not support this. In my case, my Elegoo printer did not until I made some changes to the Clipper, KLIPPER script. And that's beyond the scope of this video, but you need to know that. So anyway, I cut this thing, I sliced the thing once, I added the command to stop at layer 25, sliced it again, and then saved the G-code to the hard drive, which I then uploaded to the printer. So let's print that thing. Meanwhile, while I'm waiting for the printer to warm up, I'm going to take my servo horn and I'm going to cut it at the edge of the second hole in both of the long directions. At that point, it'll be ready for me to insert into the print. So the printer printed up to step layer 25 just prior to that and presented the part to me. I'm going to press fit the part deep down in there making sure that it is fully below the edge, and then hit resume on my printer. And the part will reload and start printing over the top of that part. Here's the top and bottom view of what we ended up with. The servo horn is fully embedded within the part, yet is flush at the bottom with the gear so that we can easily mount it on top of our SG90 servo. Finally, I 3D printed a quick rack and pinion that I designed to go along with that gear, hooked the servo up to a Serial Wombat chip, and provided power from a USB battery through one of the boards I sell on Amazon, and lo and behold, it works pretty good. So I'm very pleased with the way that this project worked out. I hope you enjoyed this video. I hope you had a little bit of fun watching it and maybe learned a little bit, or at least got the idea of what I was doing so that you can do it yourself. So if you use this project, please leave me a comment down below or a like. If you need a way to control your servos, definitely look at the Serial Wombat 18AV chip. It's an open source firmware that I do. Very capable and can do all kinds of stuff like real-time feedback control with servos, driving them based on PID, up to 18 servos on the chip, and can do things like rate control, default position on loss of communication. So all kinds of other interesting stuff that other servo control chips do not do. So that's all I have for today. Hope you enjoyed this and have fun. Keep making stuff. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.